We're now going to expand our knowledge of PDelta analysis, where we looked at PDelta static analysis in the last video. We're going to talk about PDelta buckling analysis. So PDelta buckling analysis can help us determine the smallest critical load factor that would be required to cause buckling within our structure. And it allows us to specify which load case or combination we'd be interested in looking at the buckling mode shapes for, and the buckling factors. In return, it's going to report for us a buckling mode with a buckling load factor. And that factor is essentially the factor by which we need to multiply our loads by, whatever load case it is that we're investigating. We need to magnify it by that factor in order to cause buckling according to that mode shape. Now in SRAM's PDelta buckling analysis, it is an Euler buckling analysis, so it doesn't account for things like local yielding and residual stresses, but it will give you a good understanding of the global buckling behavior. However, for a more detailed approach and more control, you can always go with a nonlinear static or nonlinear quasi-static analysis as well. Let's take a look at the model again that we used for the last exercise. And we know for now that it runs during a PDelta analysis, a PDelta static analysis. But we want to understand how close it is to buckling. So if we go ahead and click Analyze, and we choose to run a PDelta buckling analysis, which is this one down here, we can specify a number of different eigenvalue extraction methods, parameters. So there's different ways that we can extract these eigenvalues from the model, and we're not going to go into too much detail on this. It's described more in our dynamic analysis and nonlinear analysis training courses. But we can get a better understanding to see here that the Jacobi threshold method is meant for smaller models. It's going to extract all the different mode shapes from the model, whereas the subspace iteration will only subtract or extract the bottom half of the mode shapes. So if you have a single degree of freedom system, you're kind of stuck with the Jacobi threshold method, which isn't a bad thing, but you only have one option in that situation. However, we don't have a single degree of freedom system, so we don't have to worry about that. I'm going to ask for 4 buckling modes. I specified the number of iterations I'd like this eigenvalue extraction method to go through, and the tolerance. And I'm going to say that I want to look at the buckling analysis results according to my load combination, gravity and lateral. So that means whatever buckling response factor I get, or critical buckling factor I get, rather, it's going to be the factor by which I would need to multiply my existing gravity and lateral load combination magnitudes by in order to cause buckling. So I'll press OK. We're going to go through the analysis, and basically what it's doing is it's scaling up our analysis until it finds some sort of unbounded deflections. And we get a clean solution here. And you notice when we run a buckling analysis, we don't have all the usual tools available to us. It's only extracting eigenvalues. It's not running an analysis where we can look at the forces and moments within our model. We can see here that we have one tool available to us that we can use, the buckling modes tool. And if I left click on this tool, I get a little legend here, and I can select whichever mode shape I'm interested in. So I have 4 different mode shapes with different magnitudes of buckling mode shape factors. I have mode shape number 1 with a factor of 2.35. And if I animate this, I can see what that looks like. Mode shape number 2, 13. And this may actually be easier to see in S-View if I go to Run S-View. So in S-View, I can actually see these mode shapes perhaps a little bit more clearly. I can even show the object view. So I can see mode number 1, mode number 2, 3, and 4. And what these factors mean is that if I increase my mode or my gravity and lateral load combination magnitude by 2.35 times, I would get buckling with this type of mode shape. And if I increase it more than that, I would get this type of mode shape. Now, from a practical standpoint, if I increased it kind of gradually, I would never get to mode shape 2 or 3 or anything like that. It would probably collapse by the time I got to mode shape number 1. But there are reasons that we might want to see the other mode shapes as well. It's also worth mentioning that the direction that this oscillation is happening isn't really important. It's going to oscillate the same in each direction. So that's not really too much of an issue. But what I want to take away from this here is that mode shape number 1 occurs with a buckling mode factor of 2.35. So that means that if I factor my loads in the load combination by 2.36, just greater than 2.35, I should have a buckling failure. So let me do that right now. I'm just going to go to the spreadsheet window, switch to the load spreadsheet, and in the load combination spreadsheet, and I'm just going to change these mode shape or load combination factors from 1 to 2.36. I'm then going to rerun this buckling analysis for that same load combination, which I've now factored up. Now this load combination is still solving as it did before, but you can see here that the mode shape factor has changed. The actual mode shape itself hasn't changed, but the factor has changed. It's giving me a value less than 1, indicating to me that based on the amplified loading that I've now applied, we're now getting an issue with the buckling occurring. And if I tried to run a PDelta static analysis, I go run PDelta static, we can see here that we do get a diagnostic message. According to this message here, it's saying node number 3, degree of freedom 5 has an issue. That's rotation about the y-axis. So I'd have to look into that and see that this is giving me some understanding for how the buckling mode or the buckling analysis works. For node number 3, which is this joint right here, we can see that degree of freedom 5 y rotation. Basically, it's indicating to me that this thing would start to topple over with this increased magnitude of loading. And if I actually look at the deflections for this PDelta static analysis, I can see that they're extremely high, 6,000 millimeters of displacement for a relatively small structure. That's quite a lot. So this gives us a clue to how this works. It's actually looking for unbounded deflection. And we may want to say, well, if we do have this type of loading, maybe this is what we're having to deal with for this type of model, we need a way to combat that. So maybe we need to stabilize the structure some more. I can try adding some bracing to the model. So I'm just going to go to the geometry window, and I'm going to add additional members to the model. I'll add, using the member definition tool, a truss member type, and it's going to go here from the bottom left to the top right of each frame here. And I'm going to change the section here. I'm going to actually add a new section from the steel database. It's going to be an angle section, and this angle section here, I'm just going to find it from the database. It's going to be this 127 by 127 by 16. So I'm going to add this to my model, click OK, give it a different color, and click Close. And I'll simply just drag my mouse to apply it to that model. Now it's also worth at this point bringing up the fact that right now we're only using one beam element or one truss element to represent each brace or beam or column. And only for linear static analysis does one element agree with beam theory. And I'll explain that a little bit more as we go through this exercise. So I'm just going to start by running a PDelta buckling analysis. I'm not going to change anything. I still have those factored up loads, but remember before I had a buckling factor of 0.99, so when I increase the magnitude of the loads, maybe I'll get some different results. Now this is just a message to me indicating that the stiffness of my truss elements in the model aren't going to be affected by the PDelta effects. That's just the nature of PDelta and truss elements because they only support axial loads. But you notice here the influence that these braces had. It went from a mode shape factor of 0.99 to 10.96. And if I look at the mode shape animations here, I can see what they look like. So it's much different than it was before. However, let me try subdividing some of my elements. I'm going to try subdividing the columns. So I'm just going to go to the geometry window and I'm going to select just the columns. I have a folder already created for that. I'm going to break them down. I'm going to go subdivide. I'm going to break these columns into 2 links. Press OK. So now my columns have a joint at mid-height. I could then go ahead and rerun the analysis. So I'm going to go PDelta buckling analysis once again, and I'm going to compare the results. So you can see here that my mode shape 1 factor has actually gone down quite a bit actually. So it's at about 7.2, before it was around 11, and that's only from adding these additional nodes. But you may see why once I actually animate this. You can see that the animation of this first mode is really showing a lot of oscillation, kind of a sine wave shape throughout the columns, which we couldn't represent if we didn't have those additional joints where we broke the members up into multiple segments, because we didn't have those analysis nodes there. It's not that we've added a hinge or anything, it's just giving us an extra joint that we can use to integrate the results and better represent potential sine wave behavior and so on. And to us, this indicates that the lowest mode of buckling was actually strut buckling, like a sine wave, not sway buckling, which we couldn't represent with just that one element. And we can break this down even further. I can select the columns again, and I can say, let's just break this down, this time into 10 elements. So it's maybe a little bit excessive here, if I just show you how many joints we have. But it's for illustration purposes. I'm going to go to Analyze and run a PDelta buckling analysis again. And now we can see that the mode shape factor has dropped once again. What was once we had 11.0 with only 1 element representing each column. Then it dropped to 7.26, I believe, when we had 2 elements. And now with 10 elements, it's 7.11. And we can see what that mode shape looks like. It's obviously a lot smoother now than it was before, and more representative of the real world mode shape. So there's definitely an influence, and a positive influence at that, to using more analysis elements. Now this may not always be practical, it does come with a bit of experience, but you can see the impact that it has.